last video of this lecture, I want to give a whole bunch of examples from Conrad's introductory notes on modules. In particular, these all happen right around page 9, where he gives contrasts between finitely generated vector spaces and the more general setting of R modules. And I find these really helpful and think that they'll be really helpful for you in understanding how to think about R modules, assuming that you're already pretty comfortable with linear algebra and the idea of a vector space over a field. So we'll talk much more about vector spaces later on. I think the reason why Dummett and Foote don't draw some of these contrasts at this point is because they haven't introduced any of this material about vector spaces before. They sort of assume that you've seen some of it, a lot of it, but they're going to go through some of this material about vector spaces in chapter 11. So I think they're holding off this kind of comparison until then. Okay, we already saw one example. I mean, we saw an example of this non-principal ideal in z adjoint square root of -5 is a z adjoint square root of -5 module that does not have a basis. And we said that in a finitely generated vector space over a field, you always have a basis. All right, so what are other things sort of in that style? In its vector space V, any non-zero element, little v in V, gives a linearly independent set. Why? Because what would it mean to have a non-trivial linear relation? You would have an equation of the form alpha times v equals 0, where alpha was not equal to 0. But with a vector space over a field, alpha times v equals 0 does imply that alpha equals 0. So every vector v that's non-zero gives a linearly independent set. And that's just not true for general R modules. So for example, M equals z mod 6z. This is a Z module. It's an abelian group. And the subset 2 is linearly dependent. Why? Because there's a non-trivial linear relation. 3 times 2 equals 0. And 3 is not equal to 0 in the integers. All right, next example. A linearly independent set is called maximal if there's no additional elements in your module that you could add to it and still have a linearly independent set. So it's maximal in the sense that there's nothing else you can add to it to make one that's one bigger. In a finitely generated vector space V, a maximal linearly independent set is automatically a basis. It's linearly independent. All you have to note is that either it spans all of V and then it's a basis, or if it doesn't span V, there's something W that's not in the span of your linearly independent set. And if you add W to your set, then you get a larger linearly independent set. So you didn't actually have a maximal one to begin with. What are we using here is this thing that we talked about before, that the condition of being linearly dependent is the same as the condition of being able to write one of your vectors as a linear combination of the other vectors. For a general R module, this is just not true. Z is a Z module. 2 is a linearly independent set, and it's maximal. There's no other integer you can add to this set to get a larger linearly independent set. If you add an odd number, let's say x, then you have the linear relation x times 2 plus -2 times x equals 0. And if you add an even number, it's like even clearer that it's linearly dependent. But 2 itself, this is not a spanning set for Z. So this is not a basis. So this is different. This is not something that can happen. OK, so sort of a companion to this one. This is about maximal linearly independent sets. What about minimal spanning sets? So a spanning set is called minimal if when you remove any element from it, you no longer have a spanning set. So maybe you start out with some giant spanning set and you can take out some elements and you can still have a spanning set. A minimal one is one where every element there really is necessary. You take out any additional elements, you no longer have a spanning set. OK, in a finitely generated vector space V, a minimal spanning set is automatically a basis. It's minimal. Sorry, it's a spanning set, so it's definitely a spanning set. But if it's minimal, it's automatically linearly independent. So if it were linearly dependent, then there would be some vector you could take out. What vector would you choose? Well, linearly dependent means there's some vector you can write as a linear combination of all the other ones. So take out that vector, and you'll still have a spanning set. Yeah, so you didn't actually have something minimal. Okay, and in a general setting of an R module, this is just not true. Z is a Z module. The set 2 and 3 is a minimal spanning set in the sense that the set 2 itself is not a spanning set. The set 3 itself is not a spanning set. But it's not a basis because this set is linearly dependent. There are relations like 3 times 2 plus negative 2 times 3 equals 0. So before moving on, I just want to note that this use of the word minimal is a little bit different than how Dummett and Foote use a minimal set of generators. They say that if you have a module that has a finite generating set, there's some minimum positive integer d such that there exists a spanning set of size d and no smaller spanning set. And any set of size d they call a minimal generating set for that module. That is a little bit different than this description that's given here, but this is not going to be something that's a big focus going forward. So hopefully this doesn't end up being confusing. Okay, so I'll pause and erase, and then I'll continue our discussion of these contrasts between finitely generated vector spaces and R modules. We'll give one more example related to the contrast between vector spaces and R modules. In a vector space V, every linearly independent set can be enlarged to a basis, and every spanning set contains a basis. So for finitely generated vector spaces, we're going to see this in theorem 3 of section 11.1. And then there's something else you have to do when your vector space does not have a finite generating set, if it's infinite dimensional, and that is covered in exercise 11 of section 11.1. And this statement is just not true for R modules. An R module doesn't even have to have a basis. So it's not clear what this would mean. Like every linearly independent set can be enlarged to a basis. That's definitely not true if R doesn't have a basis. And every spanning set contains a basis. Well, I mean, that's definitely not true. Every R module has a spanning set, but it doesn't necessarily have a basis. But even for R modules that do have a basis, both parts of this can be false. So Z is a Z module. 2 is a linearly independent set. But there's no basis containing 2 because, as we've already said, this is a maximal linearly independent set. There's no other element we can add to it and get a larger linearly independent set. But this doesn't span all of Z, so it's not a basis. The set 2 and 3 is a spanning set for Z, but it does not contain a basis because 2 itself is not a basis and 3 itself is not a basis. And just for emphasis, this is not failing because of this condition that we have an R module that doesn't actually have a basis. Z does have a basis, 1. It's just that that 1 is not contained in 2, 3. And yeah, we already talked about this first example here. So now I just want to give a couple of last examples of things that maybe are a little bit surprising about the structure of R modules that Conrad points out in these notes. So the first one, a submodule of a finitely generated free R module need not be free. So that's some plausible sounding thing that's just not true. I mean, maybe you might believe that if you have a finitely generated free R module, that any submodule of it would also have to be free. And that's just not true. You should learn an example and keep it in mind. So we've already seen one. If R is Z adjoint square root of -5, R is an R module. It's an R module over itself, and it's free. I mean, it's cyclic. It is everything of the form something in R times the one fixed element 1 in this ring. But it has this submodule, this ideal generated by 2 and 1 plus the square root of -5, which we've seen does not have a basis. And what does it mean to be free? It means that you have a basis. You have this set A that is a linearly independent spanning set. All right, so the next example is something we've already said before, but now we have more language and we've seen more stuff, so I want to come back to it. A submodule of a finitely generated module need not be finitely generated. So the example we saw was you take R to be the polynomial ring over Q in infinitely many variables, x1, x2, and so on, and take the ideal I generated by x1, x2, and so on. So this ideal is not finitely generated. But R is a cyclic R module because it's of the form R times 1. It's everything of the form something in R times the one fixed element in this ring, 1. So this is a finitely generated, even cyclic R module. And this I is a submodule, but it's not finitely generated. And the last one I want to mention in this lecture is a finitely generated free R module of rank n, which, remember, that's the cardinality of a basis for R. So it has a basis of size n, can strictly contain a free R module of the same rank n. So you have a free R module of rank n. You look at its submodules, and it can have this submodule that's also a free R module of rank n, but is properly contained in it. So this is something that you might not believe can happen at first. So you should just learn an example and keep it in mind. If R is Z, then now we're just looking for an abelian group and then a subgroup that satisfies this condition. M equals Z to the D. This is a free R module of rank D. It's free on this set of E standard basis vectors 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1. It has a submodule, a subgroup, N, which is 2Z to the D, which is free on these things that look like 2 times the standard basis vectors. The D vectors 2, 0, 0, 0, 0, 2, 0, 0, 0, and then dot, 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 0, 0, 0, 0, 2. So you can check that, I mean, this really is a submodule. It is. And it's free on this set. And certainly, there are things that are in M that are not in N.